So one of the things that you've heard me talk about a lot in a lot of instances is I'm not a huge fan of memorizing. However, we will get to a point in the slideshow where I am going to give you a formula, and unfortunately some of you are going to write down that formula and just memorize it. The problem is that formula is very close to other formulas we've done already for the disk method, and so the reason I took the car approach in this problem is that you can hopefully understand what you're doing instead of just blindly plugging and chugging into a formula. There's also, I'm going to give you an outline of some self-talk that you can use for these types of problems. Now notice, all of the volume problems we've done so far have a few things in common. Number one, your representative rectangle is touching the axis of revolution. That's how we got a disk. It's also perpendicular to the axis of revolution. So that's what those disk problems all have in common. Now we're going to change it today. It's still going to be perpendicular to the axis of revolution, but the representative rectangle is not touching the axis of revolution, which is what you just did with the car problem. We took the representative rectangle and moved it up off the axis, and it creates a washer, hence the washer method. Big picture stuff like we did with the disk, this is what it looks like on a macroscopic scale. I'm creating a washer there that has a thickness. We're of course going to shrink that thickness down to dx. But down at the very bottom there, it gives you the volume of a washer. What you did is already work with that. You realize that I've got this big disk that you did yesterday, and then we punch a hole through it. So the volume of the washer that you created for your spacer is the volume of the disk from yesterday minus the volume of the hole. That's exactly what's going on there, except I just wrote it in a different form. Instead of pi capital R squared times W minus pi little r squared W, I factored out the W's and the pi's. Capital R, for our purposes, is the farthest distance from the axis of revolution to any point on the representative rectangle. It's usually going to be the top of the representative rectangle. Little r is the radius of the hole. Questions so far? Okay. Yeah, okay.
Is the big R like the inner or the outer?
Outer. Big R, outer, little r, inner. So another way to think of it is big R is the radius of the giant cylinder, and little r is the radius of the hole punched through the center. Okay. If we can find the volume, just like the disk method, if we can find the volume of one washer, then we just integrate and add up all the washers. And the reason we can, like I said, just subtract the cylinder because the bottom won't always be horizontal like it was in the last one. So we look at something like this. There's my little representative rectangle in that some random spot there in the curve. But notice that if I put that representative rectangle somewhere else, I'm going to get a different R value. And that's where calculus comes into play. The initial problem today with the Mercedes-Benz could be done by just about any math student. Anybody could figure that out if they could find the volume of a cylinder. This requires calculus because those values are changing depending on what spot you are on the graph. Another example, two functions, one on top, one on the bottom, get that funky red or pink area on the left, and then you spin it, you get that solid, and in essence what we're going to do is find the volume of that washer. Okay. So how do we do that? Well, we need to find two things. We need to find capital R, and we need to find lowercase r. And the thing that always holds true is still top minus bottom. So, there's the formula that I talked about. Capital R is the big radius, little r is a small radius. You square each of those because you're looking for the volume of that washer. Okay. But again, I'm not a huge fan of the formula, but for those of you that are, there it is. What I'm going to do is take a more geometric approach to it and find the volume of the big cylinder, find the volume of the hole, and subtract the two. So I'll actually solve most of these problems using two separate integrals. It's entirely up to you what you want to do. Okay? So, if we attack this problem, first thing you need to do is, if you don't have a picture, you need to figure out which one's on top. Well, this one I gave you a picture already, so we know that the square root of x is the one on top. And x squared is on the bottom. So we're going to do another problem with this cat's eye / leaf looking thing. And when we spin it, we're going to get the volume of that blue thing over on the right. Okay, so like I said, I approach the problem a little bit differently than maybe you would. What is, well, it's already in the picture. Notice that capital R is the square root of x. It's the farthest distance from the axis of revolution up to the top of the representative rectangle. Little r is the closest distance from the axis of revolution up to the bottom of the representative rectangle. It would still be the same thing. No matter where I put that representative rectangle from 0 to 1, these two things are still going to apply. Still going to be the square root of x is still going to be x squared. Notice they're not numerical values, they're equation values. Okay, so this, the reason we call it representative rectangle is because it represents any possible rectangle in this area. Okay. Anybody else? We're good? Okay, so we got that. The outer radius, square root of x. The farthest distance from the axis of revolution to the top of the rectangle. The inner radius, that's the radius of the hole that I punched through the figure. Put it into one integral like many of you will do, and you get that. One of the problems that occurs is people want to do capital R minus little r and then square that quantity. It's each individual radius being squared. You're finding the volume of each of those independent disks. Is it safe to assume that you would not have much of a problem with that integral? Yes, it's safe to assume. Excellent. Okay. Square root of x squared is just x. X squared squared is x to the fourth. Plug and chug. We got that. Okay, so I only have one washer example here because I need to get into something else which is going to get a little bit hairy. So before I move on, are you okay with this concept?
Yeah.
Okay, so now we can do problems where the representative rectangle is perpendicular to the axis of revolution. And within that, we have two variations. It's touching the axis of revolution, which would give me a disk, or it's floating above it, we would get a washer. Good? Okay, now let's revolve it around something other than the x or y axis. This is going to be fun. Okay. I'm going to try to take the KISS approach to this. You all know the KISS approach, right? Keep it simple, stupid. Correct. We're going to remember top minus bottom. We're going to remember the things I already talked about identifying whether it's a disk or a washer. And then we're just going to plow through this. Okay? So I got this. So what's going on there? Well, I've got a parabola. It's in red, x squared plus 2. I've got a line, 1/2 x plus 1. And I'm bounding a region between x equals 0, also known as the y-axis, and x equals 1, the vertical line through 1. But now I'm revolving around the line y equals 3. Yeah, this is going to be fun. In other words, my axis of revolution is right there. Oh, yeah. Okay, got the setup. Ooh, that'll be a fun exercise. Let's take 10 seconds and visualize in your mind what that solid is going to look like. Try not to kill yourself. It's like a bowl on its side with a flat bottom, but an inside rady, curvy thing with the, yeah, never mind, we don't care. So, a couple questions. Is my representative rectangle, shown here in green, is it perpendicular to the axis of revolution? Yes, so we can solve this problem. Is it touching the axis of revolution? No, so therefore we're going to do a washer problem. Okay? Everybody with me so far? Holler if I lose you. No, I haven't lost you yet. Looking at that picture, where is capital R?
It's the farthest point.
Here.
No, I don't want to.
Just draw it. You don't have to do any calculation. Just show me on the picture where capital R is. The worst that can happen is you're wrong and we all laugh at you and you have to go see your counselor.
Well, so like, isn't it like the furthest point of the rectangle?
Show me. Talk less, show more.
Okay, so I was thinking that it's from the thing. Wait, I don't want to pinch all that
Perfect.
picture. I was thinking it was from the thing to like the
Yeah.
farthest point. Oh.
If you don't mind, I'm going to clean it up a little bit because
Yeah.
that was pretty sloppy. I mean,
Yeah.
you could have, I would go with the braces technique and, get that. Good.
That's good too.
Any problems? As Noah tried to say, it's the farthest distance from the axis of revolution to the furthest point away on any part of the rectangle. Now this time the rectangle is the bottom because we're going from the top down. Okay? Where's little r?
Go.
Oh God, you might be wrong.
Oh my god.
Scarred for life.
Okay, I don't know.
What?
No?
What's wrong? No, I'm kidding. You're perfect. You're great. This message. Scarring children professionally. Thank you very much.
Since?
Everybody good? Since 1990.
Oh, can you explain why it's there? I don't really.
Hold on, let me ask my friend. Could you explain to her where the little arc came from?
Well, okay, since the black line on the top is like the practically the x-axis, so like that's why it has to be the smaller. It has to be underneath the big dot.
So it has to be one of these lines.
Yes.
Okay.
It's the closest, so using that green representative rectangle, it's the closest distance from the axis of revolution to the rectangle.
Okay.
Okay?
Yeah.
Good so far?
Great.
Awesome. Now let's talk equations. Based on this problem, how long is capital R? Okay, so stop. Hammer time. No, just kidding. We're still talking top minus bottom. So Noah did a great job of telling us where capital R is. What's the top of capital R?
1/2x plus 1. Y equals
3. Good. Okay. So, top minus bottom. The top is 3. Minus the bottom. What's the bottom of capital R? Beautiful. 1/2 x plus 1. Notice parentheses. Muy importante. See? See. How we doing? Awesome. What's little r? Good. Still adhering to top minus bottom. And as a side note, if we were doing this with y's, it would be right minus left, but we're still doing top minus bottom. That's the hard part. The rest is easy peasy. Because we want to find the volume of this thing. Don't forget to label it as a volume. I'm integrating from where to where? 0 to 1. These are half units. Yes. Sorry. Okay, so the big radius quantity squared times pi. That's the volume of the big honkin' cylinder. I'm going to subtract from that the volume of the hole. The volume of the hole would be the little r squared. How's it going? How's it?
Can you put the pie in the front?
You could, yes. I'll get there in a second. Pi dx. And I got a little sloppy with the dx. They should each have a dx, but one dx will work. And yes, I would definitely put the pi out in front right away. But what I wanted to show was, the reason I put it here is this is the volume of the whole cylinder. This is the volume of the hole. And so take the pi and put it out in front. It's a constant. Then go crazy. Now, this whole business about going crazy is just being careful. Do not multiply out a trinomial. Because what's 3 minus 1? 2. Now all of a sudden you've got a binomial that, yes, you have to multiply it out. Same is true with the back end. This is 3 minus 2, which would be 1. So my equation becomes from 0 to 1 of 2 minus 1/2 x quantity squared with a pi out in front minus 3, nope, not 3, 1 minus x squared quantity squared dx. I distributed, or I cleaned up these things. 3 minus 1 is 2. 3 minus 2 is 1. You need an x. Yeah, it doesn't matter. You can write it either way, but not minus 2 would be positive. 3 minus 1 is 2. Okay? I don't want to spend time solving the integral because I'm assuming you can do that. You can square a binomial. You can take the antiderivative of each of those terms and get your answer. Answers for volumes should always be positive. If you get a negative answer, you screwed up. Okay. Questions?
Can you F and in this?
I would. Unless it specifically says don't FN into it because your teacher wouldn't let you.
Okay.
We're all done. Get it? Do you guys know what this is? Okay, just checking. Do any of you know what this thing is?
It's a washer.
That's a wash. Have any of you ever used one of these before?
Yes.
Really? Okay, good. You never know. What?